Okay, so here we are on Unit 3, Notes 2, Function Analysis, Day 2. So we are continuing from where we left off last time, and we went through critical numbers, we went through increasing and decreasing intervals, and we went through relative extrema, right? So we did quite a bit last time, and we're going to begin today by talking about absolute extrema. Absolute extrema of a function. This is also another word for this. Instead of absolute extrema, this is sometimes called global. Oh my goodness. Global extrema. Remember that extrema just means mins and maxes. So absolute extrema is absolute min, absolute max, or global min, global max, all right? And how I'm going to start off with this discussion on absolute extrema is with the extreme value theorem, the EVT. This is another existence theorem, okay? And it's a very easy one. It's easy to forget about because it makes so much sense, all right? It's easy to forget that it even has a name because it's just so logical, all right? If f is continuous on a closed interval, a to b, then f has both an absolute maximum value and an absolute minimum value. Okay, and that's it. And it makes so much sense. If you have a closed, if you have a graph, a function that's continuous on a closed interval, I don't care what this thing does. It could do really goofy things. If it it can't go backwards. It has to be a function, but it could do lots of things. But if it's continuous on a closed interval, then it has to have a maximum value and a minimum value. Okay? That maximum or minimum could occur at two different x points, but it would be the minimum value or the maximum value of the function. Okay? Remember that maxes and mins are the y values. Okay, so it makes total sense. Now, keep in mind this. Even in this goofy little thing that I just drew, the maximum value, it has to occur either at an endpoint or at a relative min, right? Those are our only candidates. I wouldn't ask myself, I wonder if that's the absolute max. I wouldn't do that. It has to be either at an endpoint or at a relative max. Same thing with an absolute min. The absolute min has to be either at an endpoint or at a relative min. It just makes sense. So when we're finding absolute extrema, we're going to still look at the derivative because we're still considering these relative maxes and mins as possibilities, okay? So in everything we've done so far, we've started by taking the derivative, okay? And this is no different. So this is example, if I'm continuing from last time, which I am, I've just finished the last notes, we're on example 7, okay? And in this one, I'm just going to say find the absolute, I'm going to abbreviate absolute, ABS, absolute extrema, okay, of each of these, all right, of each function. So let's say of g of x is equal to x to the 4th minus 32x plus 4. Okay, now I'm going to give you some boundaries on the closed interval -3 to 3. If I didn't give you boundaries, we could still do this problem, but we may not have a max. We know that we talked last time about this x to the 4th polynomial, and I think if you remember, well, I don't know, I don't want you to remember too much about this because it would just give it all away. Anyway, let's just do this problem. We'll talk about that later. Okay, so I'm going to start off with, since we're finding the absolute extrema, I'm going to show you how to organize your thoughts here. Our absolute extrema will be at either an endpoint or at a relative min or relative max. Well, the relative min and relative maxes, that's where the derivative is 0 or undefined, right? But the boundaries are the boundaries. They're just given to you. So we're going to make a little table, okay? This is called the closed interval test, okay? And the closed interval test will always guide you in how to do an absolute extrema problem, okay? Always guide you. You may not be able to finish with it, and we'll do some like that, but you may not be able to finish with it, but it'll always guide you in what to do, all right? So on a closed interval test, you're finding x values where important things happen, okay? And you're finding, in this case, we're finding the absolute min and the absolute max of g. So g of x goes in our table. X and g of x go in our table. Under x's, I'm going to begin with my closed interval. -3 and 3, because those are candidates. This is sometimes called the candidates test. Oops. Okay. Alrighty. So those are possibilities. So those are our boundaries. We're going to put our boundaries. Okay. And then also under x, you're going to put anything that makes your derivative, in this case g prime, 0 or undefined. Okay? And those are going to go on here as well. So these, we're going to go find these first. So g prime, we're going to find g prime. G prime is 4x cubed minus 32. Set it equal to 0. Nothing makes g prime undefined, but something makes g prime 0 here. If we solve this for x, take out a 4, x would be 2. So the only thing that we need to add is 2 to our candidates test. All right? And now the rest is really easy. All we have to do is find g of -3, g of 3, g of 2, and look to see which is the biggest and which is the smallest. That's your absolute max and your absolute min. So come over here, g of -3 is going to equal -3 to the 4th minus 32 times -3 plus 4. Okay, this turns out to be, don't know why I put that parentheses there, oh well. This turns out to be 181. So that goes over here, 181. Okay, now find g of 3. 3 to the 4th minus 32 times 3 plus 4. That turns out to be a negative 11. And then g of 2. We'll have 2 to the 4th minus 32 times 2 plus 4, and that turns out to be a negative 44. So now all you have to do is look and to see which is the highest and which is the lowest. Well, this will be our max, this will be our min, okay? But we need to say that in a logical way, right? So I'm going to say G has an absolute maximum value of 181. If you want to here, you can say at x equals negative 3. Okay? It depends on how they pose the question. If they say find the absolute maximum value, then you don't have to say where it is at. You just say the value. Okay? Now, it doesn't hurt to say where it's at. It just depends on how they pose the question. And then G has an absolute minimum value of negative 44, and that one occurred at x equals 2. Okay? If they want you to justify, which they often say, justify your answers. Our justification came from the work that we did here. Okay? That's where our justification is. If you don't like that, if you don't think that that's enough, it is enough. But if you want to call it something, if you want to say since, because I always say if it says to justify, say since, why? Well, I would say by closed interval test. And the reason I say you don't have to in this case say that is because it's obvious that you used a closed interval test here. All right? So you don't have to say by closed interval test because it's right there looking at us. Okay. Number 8. H of x equals natural log of x squared on the closed interval 1 to 3. So again, find the absolute max value, absolute maximum value, and absolute minimum value of h. Okay? So if I am finding an absolute, I'm going to use the closed interval test. So on the closed interval test, my independent variable here is x. Sometimes it's t, right? And then I'm finding the max and the min of h. So that's what goes on my closed interval test. Start with your boundaries, 1 and 3. So put your boundaries there. And then leave room, because you can put anything that makes h prime. You have to put anything that makes h prime 0 or undefined. So remember, boundaries, and then derivative 0 or derivative undefined. Okay? So let's go find that. H prime here is going to equal, okay, what's the derivative of natural log of x squared? Well, that's u prime over u. Okay? We set that equal to 0. Alright? Now, before we solve this for 0, I'm going to get my values of x that make this undefined, right? And x equals 0 makes it undefined. Undefined at x equals 0, right? Normally, I would come over here and put 0 right there. Why don't I do it now? Because 0 is not in my interval, is it? So I'm not going to put anything over here that's not in my interval, because that doesn't matter. All right? Now, I finished solving this for x. If I multiply both sides by x, I get 2 is equal to 0, and that's just not true for any x. So there are no x values that make h prime 0. Okay, so there's no more x values that we need to put in there. All we have to do is find h at 1 and h at 2. I'm sorry, not 2, 3. And we're going to see which is bigger and which is smaller. So if we put h of 1 in, we'll have natural log of 1 squared. And natural log of 1 is 0. And then here we'll have natural log of 9. So 0 and natural log of 9. Which is bigger, which is smaller? Well, 0 is the minimum value here. Natural log of 9 is larger than 0. How do we know that? We know that because the natural log graph always increases. It's never decreasing. So natural log of 9 will be bigger than natural log of 1. Okay. So h has an absolute max value of natural log of 9. Okay. They did not ask for the x value, so this time I'm not going to give it to them. Since they didn't ask for it, why would I give it to them? It would just, I might write it down wrong, and knowing me, I probably would write it down wrong, so why risk it? Okay, and h has an absolute minimum value of 0 by closed interval test. But again, I don't have to say by closed interval test because it's clear. Here is my closed interval test. So I'm done. Okay? All right. Example 9. Example 9. Okay. Given the graph of f of x, I'm going to sketch you out a little graph of f of x. Given the graph of f of x and given that f has horizontal tangent lines at x equals -1 and x equals 2. State the absolute extrema on each of the given intervals. We're going to have several parts to this question. Okay, let me see if I can sketch this out and make it look halfway decent. All right, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. All right. I want this point to be at -3, 2. I'd like this point to be at -1, -2. I want to go through 1, 0, and then here I want to go up to 2, 1, and then I want to come back through 3. So let's see if I can make it through all these and make it a nice smoothish curve. We'll see. Okay, I've done worse. All right. So let's see. On part A, I want you to find the absolute max and the absolute min on the closed interval from -3 to 3. Okay? So from here to here. ignore these other, what I'm covering up. So what is the absolute max and the absolute min? Well, the absolute max is 2. It's the y value, right? So the absolute max is 2, right? What's the absolute min? Well, the absolute min is -2. Okay, let's go. Okay, let's go to another interval. What about if we open up those intervals up there? Okay, so now we're still covering these up, but now we have open circles right here and an open circle right there. Okay, the absolute min is definitely still -2. The absolute min is definitely still -2. The absolute max, though, it's trying to get up here to 2, but it can't get there, right? I cannot say that the absolute max is 2 because it will never ever get to 2. So in this case, there is no absolute max. All right? Another interval. -3 to -1. Let's go -3 to -1. So I'm covering up all that. Okay, now this is open and this is open. Okay, so what's my absolute min and max now? Well, there are none of either. No absolute max, no absolute min. Can't do it. What about -1 to 3? -1. So now we're including -1, but we're not including 3. Not including 3, so that's still open over there. The absolute max is 1. The absolute min is -2, if we're including that -1 in our boundary. Okay, what about from -infinity to infinity? Boundless. Okay, does it have a max? Give me the number that it's the maximum. Well, there is none, because any number that you give me, I can give you something higher. Okay? And infinity is not a number, so you cannot give me infinity. So absolute max, there is none. Absolute min, it goes on, it's unbounded. It's unbounded in going high and going low. So no absolute min, no absolute max. Okay. One more example on absolute mins and maxes. Find the absolute extrema of f of x is equal to 2x to the 4th minus 8x cubed plus 5x squared, all divided by x squared, on the interval from 0 to 3. Okay? Now this is not a closed interval, is it? This is an open interval. But our closed interval test will still guide us. So I still want to use the closed interval test to guide us. So I will. This is one of those cases where I can't use the closed interval test to answer my problem, but I can use it to guide me. Okay? So this 0 and the 3, I want to put it here, but I also know that x will never get to 0 and x will never get to 3. So instead of just putting 0 and 3, I'm going to put going to 0 and going to 3. And if I put going to x value, then I'm also going to be going to that y value. So whatever I get for the y value here, I have to know that it will never reach it. Just like up here when we were doing these, it'll never reach that value right here, right, and right here, if it's an open interval. So that's what I mean by this closed interval test will still guide you. You just have to know how to read it, okay? All right, now over here we need to put anything that makes f prime 0 or undefined, right? So let's come over here to f. And before you dive in and take this derivative, we can do something that will make our lives much easier. Up in the numerator, there's a common x squared, isn't there? There's a common x squared. So I can take out an x squared from every term. And now I see, oh my gosh, there's a hole in this graph. And it happens at x equals 0. Hole at x equals 0. Okay? Is x equals 0 part of my domain? No, it's not. So I don't really care that there's a hole there. I can go ahead and cross that puppy out. And if you cross that out, it's going to make taking the derivative much easier. So again, the reason we can cross it out is because we've taken care of that situation. Okay? If it was included, then I would just come over and put it on my closed interval test. It's already there, right? But now I don't even have to, now I can just go ahead and take the derivative on what remains. So the derivative would be 4x minus 8. Much easier to take that derivative than it is using that quotient rule, right? Yeah. All right, nothing makes this undefined, so we're just going to set it equal to 0. We get x is equal to 2. 2 is in my boundaries, so I put that on my closed interval test. All right. Now, I want to fill out the f parts. F of 2, that's going to be easy to do. F of 2 will equal, and here I'm putting it right in here, you guys, which I can do because everything else will cancel out, right? So 2 times 4 minus 8 times 2 plus 5. This is a negative 3, so f of 2 is negative 3. For these, I'm actually taking a limit because we're going to 0 and we're going to 3. So it's the limit as x goes to 0 of f of x. Okay, the limit as x goes to 0 of f of x, we can still put it in what remains here because of what we know about limits, right? And as x goes to 0, this is just going to equal 5, right? So this is going to 5. It'll never get there, but it's going to 5. And this last one, x is going to 3. Once again, I'm going to be putting it up here because if I put 3 here, they'll just cancel out. So put it right here. So 2 times 9 minus 8 times 3 plus 5, and that is a negative 1. So we're going to negative 1. All right, look for the highest and the lowest. Well, the highest was this 5, but it's never going to get there. So this is the highest, but it'll never get there, so no max. This is the lowest, so that is our min. Okay, I have seen this on AP exams and on my exam as a multiple choice question. okay? And it would have a variety of answers, and one of them would be maximum at 0, 5. Okay? Maybe part A would be, or answer choice A would be maximum at 0, 5. Minimum at 2, negative 3. Answer choice B, maximum, none. Minimum, 2, negative 3. That would be our correct answer. Okay? And then I'd make up whatever. Make up some more choices. Alright? Okay. Next up, concavity. Concavity. Alright. Concavity of a curve. This is a nice little drawing. Let's use this for concavity. And we talked about concave up, we talked about concave down, and we talked about point of inflection, right? Think of concavity like, and I told you about the tangent line being above the curve or below the curve. That will determine if you're concave up or concave down. Another way to think about concavity is like this. Think of the derivative right here. It's negative, but what's it doing? It is negative, but is this slope increasing or decreasing as we get closer to here? Is the slope increasing or decreasing? Well, this slope here is increasing, isn't it? The slope is increasing, and that makes it concave up. If the slope is increasing, you're concave up. What if your slope is decreasing? Here we're pretty steep, and the less steep, flat, negative, more negative, more negative, more negative, more negative. Here our slope is decreasing, so we are concave down. Alright, slope increasing, concave up. Slope decreasing, concave down. Well, slope increasing would be F double prime, right? F double prime positive. That would be the slope increasing. Slope is F prime. To see when anything is increasing, you take its derivative, right? So F double prime positive, F double prime negative. That's concavity, you guys. So if F double prime is positive for all x in an interval, then F is concave up on that interval. Okay, unlike increasing and decreasing, concavity is an open interval. Okay, it's open interval always. Okay, if F double prime is negative, then F is concave down. We abbreviate that CC up arrow and CC down arrow. We abbreviate in class, but we don't abbreviate that in an FRQ on the AP exam. Okay? Now, we also talked about point of inflection, and a point of inflection is where concavity changes. So concave up to concave down, or concave down to concave up, either one. Okay, and since concavity depends on F double prime, it's where F double prime changes signs. Changes signs. All right, let's take a look at an example here. We're almost done. All right, let's say, what are we on? Example 11. Let's say h of x is negative x cubed plus 6x squared minus 9x minus 1. And we're going to state all the intervals where h is concave up, all the intervals where h is concave down, and we're going to state any points of inflection. Okay? So, at any time I see concavity, I think double prime. So h prime is, first I find h prime, then I find h double prime. So negative 3x squared plus 12x minus 9. For only concavity and points of inflection, we don't really use f prime. We go straight to f double prime. Negative 6x plus 12. Set it equal to 0. From here, you guys, look for anything that makes it undefined or 0. But nothing makes this undefined, but if it did, we would need to put that on our sign chart as well. And by the way, we are doing a sign chart because we're looking for signs. Okay? Anytime you're looking for signs, do a sign chart. So x here is 2, and that's the only thing that will go on our sign chart. And we're doing a sign chart on the second derivative because we're looking for concavity. Okay. All right, I'm going to put in 0, and if I put in 0 for x right here, I get a positive. That means we're concave up in that section. And if I put in something like 10, I'm going to get a negative. That means in this section we're concave down. So h is concave up on negative infinity to 2, since h double prime is positive there. H is concave down on 2 to infinity, since h double prime is negative there. And h has a point of inflection. We abbreviate point of inflection as POI. I use a little lowercase o because it's only an of. Okay, at. All right. It occurs at x equals 2, but a point of inflection is a point. That's why it's a point of inflection. They don't call it the x value of inflection. They call it the point of inflection. So we need to go find the y value because we want the point, right? So we're finding the y value, so we go back up into h. So h at 2 is going to be negative 8 plus 6 times 4 minus 9 times 2 minus 1. And when you work this out, we get a negative 3. So h has a point of inflection at 2, negative 3. It's a point, so make it a point. Since h double prime changes signs there. Okay? Another way that you could be asked about concavity points of inflection. How many points of inflection does f have if f double prime is given by x times x minus 2 squared times x minus 5? This would be a great multiple choice question because the choices would be like 0, 1, 2, 3, things like that. Okay? So here they were kind enough to give us f double prime. We didn't have to go find it. So I can just take this guy, set it equal to 0. Nothing makes it undefined. Get my zeros here, so x is 0. And they factored it for me. Not only did they give me f double prime, but they also factored it for me. I love it. Those are my x values, so those go on my number line, my sign chart. Okay. Okay, if I put a negative in, like -1, negative, something squared will be positive. So negative times positive is negative, and then this would be another negative. So negative times positive is negative, and then negative times negative is back to positive. So this is positive here. So we're concave up. All right. If I put 1 in for x, 1 in for x, so positive, positive because we're squaring, and then negative. So this will be a negative, concave down there. Now, over here, if I put a 3 in, I got positive, positive, negative again. Why did this not change? Why did we just not change signs here? We couldn't say don't change signs around that 2 because that factor is being raised to an even power. If your factor came from an even, if your factor is has an even power, then the signs won't change around it, okay? If the factor has an odd power, like a 1 or a 3 or a 5, then yes, the signs will change around it. So around the 5, our signs will change. So how many points of inflection do we have? How many times did F double prime change signs? Twice. So this will be a multiple choice question. The answer would be 2. Okay, one more thing to talk about, and that is the second derivative test. So the first derivative test says this, and we've already done this. F has a relative max if F prime goes from positive to negative. We've already done that one. F has a relative min if F prime goes negative to positive. That's the first derivative test. We use it. We love it. It's nice. Okay, but what about the second derivative test? The second derivative test, it starts out the same way that the first derivative test. What it does is it determines relative mins and maxes. F has a relative max if something. F has a relative min if something else. Okay? So let's think about this, because we're going to be using the second derivative, somehow, right? So let me get a scratch piece of paper over here. So if you have a relative max, the slope is 0. It has to be. F prime must be 0 or undefined. Yeah, or undefined. What's concavity? What is the concavity of a relative max? It's concave down. So F double prime is negative. So if F prime is 0 and F double prime is negative, then you have a relative max. Okay? Now over here, oops, I said F double prime was 0. That was a mistake. F prime is undefined here. Okay? Here concavity changed, didn't it? Concavity changed. So this one, it didn't. We can't use the second derivative test for this case. All right, but we can use it for the other case. So F has a relative max if F prime is 0 and F double prime is negative. both of those have to be true for the second derivative test. F has a relative min if f prime is 0 and f double prime is positive. Okay, think about that. F double prime negative, you're concave down. F prime 0, you're right up here at a max. F double prime positive, you're concave up. F prime 0, you must be down here at a relative min. It makes sense. So this is the second derivative test. If f double prime is 0, then maybe you have a relative min, maybe you have a relative max, but we don't know without further work. So if you get f double prime to be 0, okay, and this is true, then you need to go back and do the first derivative test. Okay? So if you find f prime, you always are going to do f prime first to see if it's 0, then do f double prime. If you found f prime to be 0, and then you find f double prime to be 0, then the second derivative test does not work, and you need to go back and do the first derivative test. Okay? All right, and I have one little example. This is how you would see it. This is one way to see this problem. Let me hide my little answer there. So, okay, there's another little note. All right. Okay, given g is twice differentiable, and g prime of 4 is 0, and g double prime of 4 is negative 2/3. Which must be true? And here are the choices. Local max at x equals 4, local min at x equals 4, point of inflection at x equals 4, absolute min at x equals 4. Which is it? Well, here I see that we at x equals 4, we're concave down. At x equals 4, we're concave down. And we have a slope of 0. So we have to have a relative max, A. All right? You guys, if g prime at 4 was not 0, and we were concave down, then we'd be looking at something like this. Is that a relative max? In other words, is just being concave down enough to say that you have a relative max there? No. It has to be both. Okay? Alrighty. And that is it for our study for function analysis. Huge, 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 huge topic for us.